The next section in the book is section 12.9. You can read through this on your own if you want to. We are skipping this section. There are no problems for this section, but there are example problems for this section. Because we are skipping this section, which mainly has to do with pulleys, when you get to the review problems at the end of this chapter, review problem 10 comes from section 12.9. So just be aware when you see a problem with pulleys, oftentimes we're going to skip it. If you're practicing for the exam, you might want to skip it because it probably came from section 12.9. The compound pulley was invented by Archimedes from our last video, and he said, "Give me a place to stand and I will move the earth." Okay, so now we come to section 12.10, which is relative motion of two particles using translating axes. So one situation in which we could use relative motion is if you have someone standing on the sidewalk and someone else driving by in their car, and they're both observing a third object which is moving. So let's say this the person at point A is in their car. Let's say particle B is another car, and the fixed observer is standing by the side of the road. So car A and car B are both driving. If they're driving at the same speed, then the translating observer may say that car B is not moving because the distance between the two cars is not changing. Or if car B is going faster than car A, the observer A could give the relative velocity of car B. So that's what we're going to look at here. You can see a lot from this diagram here. Remember that the position is a vector. You can add vectors together graphically. So for the fixed observer, this is the position vector for A, this is the position vector for B, and this is the position of B with respect to A, which we write like this with the B/A in the subscript. So just by looking at this diagram, you can see that if you take vector RA and add to it the vector for the position of B with respect to A, you should get the position of B. That's in this equation here. The notation is rather handy because the subscripts are just telling you what position, what object you're giving the position of. But if you look at this equation here and just look at the subscripts, which doesn't really mean anything mathematically, but you have an A here and you have an A in the denominator there. So if you pretend that this A in the numerator cancels with this A in the denominator, then you're left with a B in the numerator here, which is what you have on the other side. Okay, so it's just easy to keep track of the subscripts that way, even though it's not real math. Same thing for the velocity. If you have the velocity measured by observer A, if you have the velocity of person A measured by the fixed observer, and the velocity of person B measured by the fixed observer, and the velocity of B measured by person A, these two vectors, the velocity of A and the velocity of B with respect to A, give you the velocity of B with respect to the fixed observer, just like the equation that we had for the position. Oh, and we have two different coordinate systems. So we have the XYZ coordinate system for the fixed observer, and then for the translating observer, it's a primed coordinate system. So we have X prime, Y prime, Z prime. So the primed coordinate system is moving. So the origin of the XYZ coordinate system is fixed. The origin for the primed coordinate system is moving. And that is what this vector here is, from the origin of the fixed coordinate system to the origin of the translating coordinate system. Okay, and then we have a similar equation for the acceleration. And so you can read through that on your own, and in our next video we will look at some example problems.